Hi everyone, thank you very much for coming. My name's Gordon Brown. I'm a senior software engineer at CodePlay Software. I'm going to be talking to you today about defining a unified interface for execution. The talk aims to last for about 45 minutes, so there should be plenty of time for questions at the end. First of all, the usual disclaimers. The slides that I'm presenting today are contributed by myself as well as others at CodePlay, as well as those in standards bodies such as Kronos, C++, and any views represented in the slides are those of me myself and not necessarily those of CodePlay. So who are CodePlay? So CodePlay are a small tech company in Scotland. We develop heterogeneous compute solutions for semiconductors. So we build compilers, debuggers, runtimes, and other tools for heterogeneous architectures such as GPUs and DSPs. We do this based on open standards like OpenCL, CppCon, and Vulkan. We target a range of different industries like automotive, safety critical, machine learning. So a little about myself. I've been with CodePlay for about 5 years now. During that time, I've been working on something called CppCon. So this is our implementation of CppCon. So CppCon is an open standard for C++ programming on heterogeneous systems. And I was also heavily involved in contributing to the standard itself. If anyone's interested in CppCon, I did a talk last year at CppCon. There'll be some more information on that. In the recent year, I've been more involved in the C++ subgroups for executors and heterogeneous computing. And executors is more what I'm going to be talking about today. So a couple of disclaimers before I start. The proposal that I'm going to present today is still a work in progress. Although we've largely reached a consensus on the design, there's always a chance that things will change between now and finally making it into C++. And also, as I mentioned, my background's in heterogeneous computing. There's a very diverse range of use cases that motivated the executor's proposal. So don't claim to be an expert on all of them, but we'll try to give a high-level overview of these. And also, and finally, I wouldn't be able to stand up here and present this without all of the hard work that's been done by everyone in the executor's subgroup, as well as those in SG1 and SG14 that have been contributing to this work over the last years. So the agenda for the talk today, I'm going to start off with introducing I'll start off with a brief history of the executor's proposal, show some use cases that motivated the executors. Then I'm going to show the overall design philosophy and how it looks, and then I'll show you some examples. Then I'll finish off with a look at future work, so looking at what we're still working on, what's still to come. So first of all, what are executors? So the elevator pitch essentially for executors is in C++17 we have several control structures now for executing work, things like std invoke, std async, and parallel algorithms. And traditionally these control structures have always executed sequentially on the CPU. However, recently many implementers have wanted to take advantage of parallelism, heterogeneous computing, and network computing on a range of different architectures such as GPUs, embedded CPUs, DSPs, and other accelerators. And this is usually done up until now with third-party APIs and standards such as like CppCon, OpenCL, CUDA HCC for heterogeneous, OpenMP and MPI for distributed, some libraries for C++ multi-threading, and things like BoostASIO and the networking TS for network computing. Our executors aims to provide a unified interface for writing generic code in order for executing work that can be implemented on top of all these different standards and all these different resources in a standard way that can be used by all these different control structures. So a brief history of the executor's proposal. So the very first proposal came in 2012. So this is quite far back. So this idea has been going around for a long time now. Between then and early last year, there have been a large amount of papers proposed for executors with many different ideas and approaches. And these kind of sort of centered on these four main proposals here. I won't go into any detail on them, but if you're interested, you can check them out. And these essentially show the main motivations and main proposals that kind of led to what we have in the proposal that I'm showing you today. And shortly after this, in the ULU 2016 C++ standards meeting, the C++ standards committee decided to form the executors subgroup. So the aim of this group was to bring together all the interested parties and with the different use cases and try to come up with a single unified proposal for this. And this is where I got involved in executors. So I was invited to join this group as the sort of representative of the open standard heterogeneous computing use case. And over the last year, we've put together several papers and got a lot of feedback from the committee. And the most recent papers are these two, the Unified Executors Proposal for C++. This is sort of the technical document that describes the wording of what the meat of the proposal. And then the design document is the kind of explanation of how we came to design decisions that we made and sort of some examples of how you could implement them, things like that. So we feel we're getting quite very close to consensus on the design. We feel like we're moving very close to being able to create this executors TS, so the technical specification for executors. So that's why I'm here today to present this. So what is execution? So the interesting thing about C++ is that the answer to this question would range greatly depending on who you ask. So if you were to ask someone who works primarily with multi-threaded applications, they would say static or dynamic thread pools, std async, launch policies, work that's executed on standard threads. If you were to ask someone doing network execution, they would say network devices, things like boost ASIO, networking TS, one-way communication, and work tracking. If you ask someone doing parallel execution, they would say things like the parallel algorithms, vectorization, bulk execution of multiple threads, and channeling a return value for algorithms. And finally, if you were to ask someone that does heterogeneous or distributed computing, they would look for discrete, non-CPU architectures, managed execution resources, and task graphs. So the problem is if everyone has different idea of what execution is, how do we define a unified interface that works for everyone? The problem is if everyone just pulls in favor of one approach, you never reach a consensus in this unified design. So essentially we need to find a kind of a common ground, something that all of these requirements have that we can build from. Essentially that's all of these use cases require the ability to execute work. Essentially the idea is being able to execute a callable object. Now, this might seem very trivial, because you think C++ is already capable of executing objects. But this can serve as a kind of foundation in order to build upon, in order to provide this unified interface to give all of the features that everyone needs. So the first thing that we needed to do to define executors is to establish a sort of topology of execution. So we need to define the various components of execution, what they are, how they relate to each other, and the terminology for describing execution. So this starts off with the instruction stream. So this is what I was showing a moment ago, this callable object. So an instruction stream is essentially just any callable object that can be executed. Then you have lightweight execution agents. So lightweight execution agent is essentially any thread of execution. So this could be a standard thread, or it could be any other form of thread, so like a GPU thread or anything else. And essentially, a lightweight execution agent executes the instruction stream. Then you have what's called an execution function. So an execution function executes the instruction stream on one or more lightweight execution agents with a particular set of properties. These properties come from the executor. So executor is essentially the main component of the executor proposal. Essentially, this is what describes where, when, and how work is executed. So the executor can spawn one or more of these lightweight execution agents through their execution functions, each calling this instruction stream. Oops, jumped ahead a bit. So next is the execution resource. So the execution resource is essentially a hardware abstraction. This describes the underlying resource that your work is executing on. So this could be something like a CPU thread pool or a GPU context or anything else. The final component is that kind of brings everything together is the execution context. So execution context it does a few things. Firstly, it's essentially an instance of an execution resource. So it manages an underlying resource. And the next thing it does is it's responsible for managing all of the lightweight execution agents that are executing on that resource. And then finally, it provides executors that can be used to execute work on that resource. So there's not much to show at the moment, but I thought I'd show a very, very simple 3-line example of the general idea of this. So here we have first line, create an instance of an execution context. From that, you can use this .executor, which returns an executor that can execute work on that context. And then from there, execute. This is an example of an execution function. And inside that function, we have this lambda object. This is an instruction stream. And you might notice that the components that I didn't mention, the execution resource and the execution agents. So these aren't represented as objects in code. These are more the underlying resource abstractions of the hardware that's executing the work. So these aren't represented directly as objects in code, but they are represented through properties of your executor and your execution context. So the next thing we had to do is once we had this kind of topology of how to describe each execution, we had to establish what the different bifurcations of execution were between the different use cases. So essentially, if you imagine all of the different possibilities that executors could have laid out in a hierarchy, a tree of different executor types, this is sort of showing where the different options split off. And so essentially, we came up with three main properties of execution. These are the sort of the main properties that describe the semantics of execution. There's more properties as well that I'll get to later on. These are the main ones. So the first one is cardinality. So this essentially describes whether an execution function executes a single execution agent or multiple execution agents in bulk. So the single cardinality use case, this comes from control structures such as the invokes, the async, where you want to do task parallelism. You want to execute a single task once and you want to maybe synchronize with it. The bulk cardinality comes from the use case of the parallel algorithms or heterogeneous distributed computing, where you want to launch multiple execution agents in parallel and maybe parallelize them or vectorize them. The next property is directionality. So this property essentially describes whether or not your execution function provides a channel for returning a return value or an exception, as well as synchronizing with the work. So these are called one-way directionality and two-way directionality. And essentially, this boils down to whether or not your execution function returns a future. So the one-way directionality use case, this came from the networking TS, where it was important to be able to do essentially fire and forget execution, where you launch the work and the work is handled by the receiver. You don't necessarily need to synchronize on it. The two-way directionality use case came from things like async, that needs to be able to return a future, or parallel algorithms that need to have a return value, essentially. And then finally, there's the blocking guarantee. So the blocking guarantee essentially describes whether or not your execution function will block the caller thread on the execution to complete. So there's three different options. There's possibly blocking, always blocking, and never blocking. So never blocking essentially guarantees that your execution function will execute asynchronously. So this means that it'll return immediately, but the work will run in the background on some other thread. Always blocking guarantees that the function will block until the work is complete, which means when it returns from the execution function, the work is already complete. Possible blocking is for the case where you don't necessarily prefer one or the other, and either is fine. So it's the lower guarantee of the three. Okay. So now that we have the different properties that define the sort of the semantics of execution, we need to look at what the actual execution functions are. So these are made up of two of those properties. So you'll notice that the blocking semantics property doesn't change the interface, it doesn't change the execution function. It's only the directionality and cardinality that does this. The blocking guarantees property does change the semantics of the function, it just doesn't change the interface. So here we have the combinations of one-way and two-way and single and bulk. We have 4 execution functions: execute, two-way execute, bulk execute, and bulk two-way execute. So you might wonder why there's 4 different functions, and we don't just have a single function that behaves differently depending on the properties. There's a few reasons for that. The first is that they all have very different semantics. The second is that they all take different parameters, and they have different return values. So this was one option that we were considering, having a single execute function that behaved differently depending on the properties. However, it would be very difficult to provide diagnostics for when you used it incorrectly. And finally, we also wanted to be able to allow executors to provide all 4 execution functions. So in order to do that, we wanted to have 4 unique functions. So I'll give a little example of what these look like. So first of all, this is the single one-way executor. So essentially you create an executor and you call execute. It takes a single parameter, it's the instruction stream. This is executed once. And then the next one is single two-way. So this is very similar to the single one-way. However, here it returns a future. So the future has the return value or exceptions, and it can be synchronized with. So here you'll notice that it has the returns a value. So this is because the return value of the function is then propagated back to the future. The next one is bulk one-way. So this one's a little more complicated. So it takes 3 parameters. First one is the instruction stream as usual. I'll get to the parameters of the lambda there in a moment. The second parameter is shape. So shape essentially describes the iteration space that you're going to execute your execution agents across. So for example, that shape could say I want to execute this instruction stream 1,000 times. So I'd execute that 1,000 times in parallel. And then shared factory. This is essentially a function object that returns an instance of a shareable object, a shareable type. And that's then passed to every iteration of the bulk execution as an object that can be shared between the execution agents. This is very important particularly for when you're running in parallel or for heterogeneous computing, where this can be represented by local memory, which is often very much faster to access. So to go to the parameters inside the lambda here, the first one is index. This is the current index into the iteration space defined by shape. So shape said I want to execute across 1,000 execution agents. Then index would be 0 to 999 for each of those iterations. And then S is the instance that's returned by shared factory passed by reference, that you can access it in every execution agent. Finally, you have bulk two-way. So again, this is very similar to bulk one-way. The main difference here is that there's an additional parameter called result factory. So because we're launching multiple execution agents in parallel, we need to handle the return value that's propagated to the future slightly differently. So the way we do it is the result factory is very similar to the shared factory. It returns an instance of the shareable type that's then passed by reference into the execution function.
It looks like a typo that I obviously spelling index on both the one way and the other.
Yes, sorry, that is a typo. So index should be I. Yep, I think I shortened the slides, but then forgot to change it. Thanks. Sure.
Is the index always a size t, or does that type depend on the shape type?
Yeah, so that's a good question. Yeah, so the shape type and the index type are actually defined by the executor itself. So for this example, I've used a size t just to keep it one-dimensional and keep it simple, but that is defined by the executor, so it could be multi-dimensional. The future type is also defined by the executor type as well. So the executor could have its own future for doing additional things.
Are those lambda captures
That's just. So there's nothing actually being captured here. It's just a force of habit, I think. Yeah, so essentially the way the result factory works is, so you pass this, similar to the shared factory, you pass this instance into every iteration of the bulk execution, and then the writer of the person who's writing the actual instruction stream decides how the return value is decided. So it may be decided by one particular execution agent or a result of multiple ones. Okay. So as I mentioned before, in addition to these first three properties, there's multiple other properties that we're defining. The idea of the current design of executors is that it's a very sort of policy-based interface. So there'll be a set of standard policies, but it's encouraged that implementations will have their own properties for doing things that are more particular to that resource that maybe are not so standard. So here's the current. So first of all, these are the properties that you've seen already. So single, bulk, one-way, two-way. So essentially, single executes instruction stream once, bulk executes multiple times. One-way doesn't return a feature, whereas two-way does return a feature for the value or exception and synchronization. And then you have possibly blocking, always blocking, never blocking. So it's may or may not, always or never blocks the caller thread on the execution to complete. So one thing to note about these is these first four properties are the only properties which modify the interface. And this is because they change the execution functions that are available. And also because of that, these properties are the only properties which are additive. So for example, if you had an executor that was single and one way, and then you requested that as bulk, so I'll get to customizing executors in shortly. If you were to request that this is now a bulk executor, it adds that to it. So it's now single, one way, and bulk. The same with if you said two-way, it would now be single, two-way, one-way, and bulk. Whereas the other properties are all mutually exclusive, at least in the ones that we've currently defined. So some of them are for toggling features on and off. Some of them are for choosing one of multiple choices of guarantees. So the other properties that I've not mentioned so far are these. So I'll go over these quite quickly. So the thread mapping semantics property essentially describes how the execution agents are mapped to threads. So the common one would be thread mapping. So this essentially means all of your execution agents are mapped to a std thread. Another one is new thread mapping, which essentially means that every execution agent will be mapped to a new std thread. So it'll always be launched on a new thread. Another one we have with a slightly lower guarantee is the other execution. So this allows you to map to something that's not std thread. So for example, a GPU implementation would use that because it can't make the same guarantees that you have with std thread. The bulk execution guarantees. So these are, if you're familiar with the parallel algorithms, these essentially reflect the properties of the execution policies. So unsequenced, sequenced, and parallel. So essentially this is what this property specifies. So that guarantees the relationship between the execution agents. Caller forward progress. So this is a property that essentially describes the forward progress guarantees between the caller thread and the execution agents that are being launched. And this can be quite important for guaranteeing when the function is executed. Continuation specifies whether the instruction stream should be executed as a continuation of another task. The future work submission is an interesting one because this essentially is more of a hint. So this tells the underlying execution context that you still have work to submit, even though there's nothing on the context at the moment. So it can be used, so for example, if you have an execution context that may shut down at some point, you can use this to tell the execution context, don't shut down yet, there's still more work coming even though I've not provided it yet. So that property is more of a hint because it's quite dependent on the execution context. And finally, there's the allocators. The allocator is a type that you can specify that's used for allocating memory from the instruction stream if that's necessary for the implementation. Good. So the next part is, now that we have all these properties and we have the executors, it's very common that users will want to customize their executor. They want to request particular properties of their execution. And it's also quite important for library implementers to be able to guarantee certain properties of the executions. They may customize the executor further in order to enforce certain properties. For example, std_async requires certain properties, so an implementation of std_async would guarantee certain properties in order to enforce what the standard guarantees. But we'll get to have an example of that later on. So the way this works is we have three what are called customization points. So there's require, prefer, and query. So the first one, require, so what this essentially says is that you pass it an executor and a series of properties. And what it'll do is it'll return a new executor that's able to fulfill those properties. If it can't do it, then it'll result in a compile time error. So this is very important when you want to make hard compile time guarantees that your executor will do what you want it to do. Prefer is slightly different. So the way prefer works is that it also takes an executor and a number of properties, but it may or may not return an executor that can fulfill those properties. So what it essentially does is if require would succeed, it would compile, it must do that. If it doesn't, then it is free to return the original executor as it is without modifying it. So this is quite important in the cases where you want to say you're not. It's more of a hint or a preference. You don't necessarily need those properties, but it would be ideal. Or in the case where you may want to modify the properties of the executor dynamically. Finally, the query property. So this is when you want to query the current value of a property. So unlike the other customization points, this only takes a single property and an executor, and essentially returns the current value of that property for that executor. So one important use case of this is for after using the prefer. So you can use it to query whether or not the prefer customization point gave you the executor with the properties that you're asking for. Hi. Sure. So generally, the idea of prefer is that it will. Sorry, this one. Sorry. Yeah. So yeah. Sorry. So the idea is of prefer. Repeat the question first. Oh yeah. Sorry. So the question was he was asking me to reiterate the how prefer works. So essentially, so the way it works is if require would succeed, so if require would compile, then prefer is guaranteed to do the same as require. So essentially, it's like it tries to require, but if it can, it will return the original executor.
If it can, it will return the different executor.
It'll likely return.
That's not on the slide.
Yeah,
there's three cases. There's 3 cases. I mean, 2 of us.
The success case is not listed.
Oh, sorry. Yeah. So to iterate, so if require would be successful, it must return what require would. So it would return the executor with the properties that you've requested. If that wouldn't succeed, then it returns the likely the original executor. It's unchanged. Hey.
Like the original. So it's allowed to fulfill as many of the properties as it can.
Well, it would be the original executor unmodified. So if it can't fulfill the properties you've asked for, it would return unmodified. Yep. And that's where one of the uses of query comes in, is that after you've called prefer, you may not know whether you got what you asked for. So query can be used to query, say, if I asked for something, did I get it? So I've got an example of that here. So the first example is of require. So we have a one-way executor, and then we call require with the executor and the two-way flag. And this returns a new executor type. So essentially this is saying that I want this executor to provide two-way semantics. The executor that returned, because it's require, if this compiles, this is guaranteed to succeed. So you can call two-way execute. Whereas with prefer, say we have possibly blocking executor, we'd prefer that this is never blocking. So you can say prefer, and this may return an executor type that has those properties, or it may not. So query can be used. So if we have the same example here, we have possibly blocking executor, and then we prefer it to be never blocking. then we can do a query to say, is this new executor actually never blocking? Because then that can be used to maybe change the scheduler or the way that you're executing.
Is that concept or something? So that's because this seems like type information, right? And like you want to query that maybe also like a compile time, like that make decisions based on that.
So this can be compile time, but it may not be depending on the implementation. So some implementations may want it to be dynamic information. Okay.
For the first case, for the required,
Sure.
what happens if it cannot fulfill those requirements? You just throw, or?
So for require, if it's not able to fulfill the requirements of the properties, it will fail at compile time.
What if it doesn't know that?
So that's where prefer can come in. So require is used for when you're able to determine the semantics of your executor at compile time. Prefer is more useful, can be used for when you want to do it dynamically. So as that could be quite important. I've got the next section covers that in a bit more detail. Oops. So the next part, the last part of the design is the polymorphic executor. So the idea of the polymorphic executor is that these two functions, require and prefer, can either return a static type, a static executor type, or they can return a dynamic executor type. So essentially a wrapper around an executor. Now, first of all, the polymorphic executor is required to provide all 4 execution functions. So it has to provide the whole interface because it's dynamic. It doesn't know which properties it can fulfill. So the benefit of this is, so in this example, so you have a scheduler with a 2-way executor. Then here we want to prefer that this 2-way executor is never blocking. So here, so we call prefer and then we assign it to a new executor and then we use it. There's a couple of problems with this. The first is that the statically typed executors can't be stored generically in a container like this. So for example, if you want to modify it in line, you can't do that. You always have to return a new type. So essentially, if you ever want to modify the behavior in an executor, you have to return a new type, and then after that's used, that's discarded unless it's kept later on. So the other problem with this is that if all executor types were statically typed, an implementation of prefer, so the result of prefer would have to be known at compile time, because you'd have to know what the return value is. It would have to be some static executor type. And this causes a lot of problems this would cause problems for implementations where it's important to decide whether these properties are supported at runtime. For example, if you're cross-compiling for another system, or you're running generic code that you may not know the architecture that you're going to be executing on or the properties of it, you need to be able to determine that information at runtime. So the way to fix this is the polymorphic executor. So replace the 2-way executor with this polymorphic executor. And first of all, now this is a generic executor type, and the polymorphic executor can be assigned to and constructed from any valid executor type. So here, rather than creating a new executor, we can assign the result of prefer to the existing executor. So we can modify it in line and keep that behavior. Additionally, because prefer can now, rather than returning a static executor type, sorry.
Is this being implemented using type erasure like standard any or standard function, or is there some other expected?
Yeah, it's a common implementation. So it would be type erasure on the executor to have another static executor type inside. Yeah. Hi, yes.
So how do you handle the fact that different executors have different functions, different signatures?
So the question was how to handle different executors with different signatures. So this is for when you have the polymorphic executor type.
Yeah.
So generally the way this is work is, one thing you can do is you can query the executor to say, can you provide these functions? So there's one thing I don't show here is that at compile time, you can query using traits to see whether or not they're available. For runtime, you can use the query function for querying.
The executor is a single, the polymorphic executor is a single type, so it can only have a single set of functions. What is that set?
Yeah, so the question was, it might only have a subset of the functions.
The question is, what functions does the polymorphic executor have?
So the polymorphic executor has to provide the whole interface, but it may not support all of them because the executor inside may only have certain properties. So in that case, if you called an execution function which isn't supported, it would throw a bad executor exception to sort of say you're trying to do something with this polymorphic executor that's not supported. Yeah. So the other benefit of having this polymorphic executor is that prefer, as an implementation, can return the polymorphic executor, which means it can decide at runtime whether or not the properties you've asked for are supported or not, which could be really, really important. Yep. You sure?
About to execute returns of future. What is the relationship between the lifetimes of the future object and the executor object? If the future outlives the executor, and then you call .then on the future, you want, presumably, that task to be scheduled with the same executor, which may or may not still be alive,
yep.
Right?
Yep. So the question was, if you have a future type that outlives the executor, then where is that executed? So it's actually a really interesting question. This is one of the things that that are still quite heavily debated, and this is part of the proposal is the execution context. So essentially, what you'd want is an execution context underneath which handles the actual execution. So even if an executor is destroyed, the execution context can still continue to execute work. So a future would likely have a handle to the work associated with the execution context. So it could be something like a thread pool. So if you execute work on the thread pool, that future is then tied to the result of that, the work on that thread. So obviously, if you destroyed the thread pool, then that would likely throw an exception of some kind to say, you're trying to continue work on something that's a resource that's no longer available. Generally, that's the way that we would see it working. So the next part of the talk is I'm going to go over a few examples of executors and what they would look like. So when I was writing this, I wanted to split it into sort of three different sort of target audience. First of all, there's those who would actually want to implement executors. So they want to know like, how would you actually write an executor, an execution function. There are those who implement libraries that want to use executors. And then there's actually users who will be using these executors in interfaces like std-async. So I'm going to go through an example of each of those. So the first one is I'm going to show a very naive implementation of an executor with a two-way execute. And I say naive because I have to keep this implementation quite short so that it'll fit on a slide. So essentially here we have the two-way execute function. So it takes a function object by forwarding reference and returns the result of the function. So the first thing we do is we have a using declaration to the return type just to shorten the code. We create a std promise, and then we get a future from it. So this is the promise that we use to trigger that the work is complete, and the future that will return from the function so that you can synchronize with it. The next thing we do, we spawn a thread, move the promise inside, and then we create a try-catch block. Inside the try, we call the function that's been passed in, and then we take the result and assign it to the value of the promise. If there's an exception thrown, we then catch that exception and set it on the promise as well. And then here we detach the thread and then return the future. But obviously, as I said, this is a very naive implementation. You wouldn't want to detach the thread like that because essentially the future that you're returning is not tied to the thread, it's actually tied to the promise. So you could run into situations where technically the value of the promise has been set, but the thread is actually still being context switched and it's still running somewhere. So it's a very naive implementation. It's not very performant, but it's in order to fit onto a slide. So essentially what you'd want to do is use something, spawn a thread onto an underlying execution context, like a thread pool. So this function would likely have a link back to its execution context, and you would spawn work on that context, and then return the future to it. So next, using that executor, I'm going to show how we could implement std-async. So here's the existing function call for std-async. So it takes a function by forwarding reference and a number of arguments, and then returns the result of that function called with those arguments. Now, in order to adapt this for using executors, we simply add another parameter. So the first parameter now becomes an executor. So this now says, I want to run async, std-async, but on this particular executor. So first of all, as I mentioned earlier, certain C++ control structures, such as state async, will require certain guarantees about behavior. So here we do a require to essentially guarantee this is a single two-way, never blocking, so that runs asynchronously. Now, the other overloads of state async would involve like launch policies, and these policies can also be managed by the other properties, but this is the simplest case for now. So the next thing we do is we take this new executor, and then we call two-way execute, and then we take the future. And inside that, we call the function and forward on the arguments. And then we return the future to that. Finally, if you wanted to use an executor, so if you're just interested in using executors for running on something like state async, here we have a very simple example doing a factorial computation using state async. In order to use this with executors, you simply pass the executor. It's as simple as that. Say, for example, you wanted to use this on another executor on another device, maybe even something like a GPU. Essentially, from the interface perspective, it's as simple as that. So in reality, obviously, if you're running something like a GPU, there's other considerations to take into account. There's the performance considerations of the way you write your code. There's potential limitations about what you can execute. But from an interface perspective, it's essentially as simple as just changing the executor that you use, and it'll then run on that resource. Okay. Just get a drink. So the last part of my talk will be on future work. So this is things that I felt we're still working on that haven't quite been solidified yet, but they're kind of work in progress. So all of these things are not necessarily what will be decided on. This is kind of to give you a preview of what we're currently thinking. The first one is the execution context and resource. As I mentioned in the current proposal, this isn't defined in a great deal of detail because there's a lot of different kinds of execution context and resources, and it's very difficult to define the sort of the lower bound guarantees of everything that they have to provide. But in the current proposal, we do provide an example of what an execution context would look like. So here we have static thread pool. So this provides, it has an inline class for the static thread pool executor. It provides the 4 execution functions. And then you have a function for returning the executor, and then an attach, stop, and wait for managing the work from the thread pool. This is just an example of an execution context. There'll be many other different kinds of execution contexts for different kind of resources, and they'll all likely behave very differently and provide different interfaces. The next is futures and continuations. So if you remember back to this table that I showed you, the different execution functions. So this is actually a lie. There's actually a little more than this. There's, in addition to one way and two way, there's also then, which provides then execute and bulk then execute. And these are used for adding continuations onto previous tasks that have been executed. So the reason that I left this out of the main part of this presentation is that this work is very heavily based on existing work in futures. So there's a lot of work in the committee about deciding how futures are going to look and how they're going to work and the different types of futures. And this work's very based on that. So we're still debating on how this will look. To give an example of what it would look like, though, just if you're interested. So here we have a two-way executor. We call two-way execute and return a future. So what you can do with this is instead of just assigning the future, you can then call .then execute on this. And then you can call another function. The way this will work is that the future that's returned from the first task will then feed in as a predicate to the next task. So when that future is satisfied, the next task will start. So it allows you to chain multiple tasks together in task graphs. So this may not be what it'll look in the final thing. Oh, sorry, there's a question.
So in the, I think it's the current CTS future, experimental future has a member function .then. It's not called .then execute. So what's the relationship between those? So this is the function that's would be provided by a future that supports executors.
So this is one of the reasons why it's still kind of a work in progress. We need to find a way to bring these ideas together so that the executors work seamlessly with future types that are being defined in the concurrency TS.
So you're discussing changes to future to support executors?
Yeah.
We need a new kind of features, and that is not being discussed. The blockchain that you're talking about in the concurrency TS is related, but it's not the same. It's not the same. It's not going to be the same as this. So the result is that we're looking at. So even here, the futures is a placeholder actually of a new kind of futures. Not the concurrency TS future. Definitely not good features.
Yeah. Yeah. So the current futures that are defined in the executor's proposal don't relate directly to the futures in concurrency TS, but we do want them to. So this is an idea of what it could look like, but it'll likely take a different look when it's finally decided upon. Next is that for those of you who are familiar with the concepts TS, you might have noticed that the word require sounds very like requires. And this was pointed out, and it does cause a lot of confusion as to whether or not require is a concept or whether it uses concepts. So we, although require does match what we wanted the require customization point to do, we're now considering different alternatives. So enter the bike shed. We have many different ideas for names. The most popular at the moment seems to be transform executor and try transform executor. Essentially describe the fact that you're transforming executor into another type, or you're trying to transform an executor. It may, so prefer would be try transform, because it may transform the executor or it may return the original if it's not successful. This is still being debated. This is very, very recent, like last couple of weeks, so it's not been decided on at all. Sorry?
What do you guys think?
This isn't actually all of them. It's just the best ones that I picked out from the chat that I could fit on the slide without being too small.
Some of the words on the left have history.
There's a suspicious lack of past tense, since you're actually returning a different object and not modifying the original.
Okay. So the point was that maybe we should describe it as a past tense because you're returning a different executor type.
And not modify.
I see. So you mean for the prefer? Yeah.
I mean, transformed instead of transformed, right? Because you're not applying it to the original object.
That's true. Well, the way that we're thinking about it is that transform reflects the act of transforming the executor. But that's a good point. You could use it to describe this as the returned executor would be a transformed executor.
It's sort versus sorted.
Yeah. Yeah. Hi.
So one bit of feedback on your horrible colour scheme here. All terms under prefer are far too busy with all the underscores and everything. There's not a single simple one there. Whereas under the required one, they're all possibly reasonable. There's a real asymmetry there.
Yeah, so the point was that the ones on the right hand side here, they're very long and a lot of underscores. They're very wordy. Yeah. Sorry.
So I actually want this term to stick out when I saw it, because it's doing something that is potentially weird, and you really want people to notice it. Like we interpret cast. Speaking of interpret cast may be another possible name for this. Because what kind of casting?
Yeah. So once we kind of opened up to different names, we got a whole lot of different ideas and names flooded in about potentially different ways of describing what it's doing. That could work. Hi.
Just to clarify, the require kind of function would not apply if it's not as well.
Yeah. So the question was whether the require function or whatever it will be called is won't compile if the properties can't be supported. That's right. Yeah.
On the context.
So sorry.
As a definite context, can I use it in the if I want to do SPNI?
I believe there would be. Yeah. I believe there would be a context per interface. Hi.
What's the difference between
So the question was, what's the difference between require and prefer on the polymorphic executor? So this is an interesting question. So the require could still return a polymorphic executor, but the actual calling of the function has to be resolved at compile time. But it can still choose to return a polymorphic executor if it wants. Whereas prefer doesn't have any requirement to fail at compile time.
Won't require on the polymorphic executor always return polymorphic executor?
Or can
Yeah.
Can the argument to require be a polymorphic executor? Or do you need a more specific?
Yeah. So the question was, can the argument to require also be a polymorphic executor? It can, yeah. So you can have a polymorphic executor and then require. Actually, no, that's a good question. No, yeah, I think you're right. Yeah, so I think, yeah, that's an interesting question. I think maybe you wouldn't be able to use a polymorphic executor as a require. So I think if you're doing compile time guarantees for the properties of executors, I would have to stay at compile time. So the implementation could return a polymorphic executor, but it's unlikely to, because then you wouldn't really be able to do much with it. Yeah, so that's a good point. Yeah, thanks.
But that means that you can't use a polymorphic executor async, because that means require.
Yes, so the question is, would you be able to use a polymorphic executor for state async? I think, yeah, in that case, you wouldn't be able to use a polymorphic executor because it would have to be compile time. That's an interesting comment. So we'll have to think about that. Thanks. Did you? Okay. Awesome. So the last future work that we're looking into is so one type of executor that you could create is a one-way executor that is never blocking. So in this case, if you imagine the way this would work is it wouldn't return a future, but it would launch the work asynchronously, which means you're essentially firing, forgetting about the work, but then having no way to synchronize it. So the way this is generally handled is that you'd have an execution context in that case, like a thread pool that would do the synchronization, that would wait on the result. However, the one thing that doesn't do is it doesn't cover how you'd handle exceptions. So in some implementations, you may just want to drop the exceptions because you're not interested in exceptions within the instruction stream that's executing. But if you are interested, the suggested approach that we're looking at for this is that the execution context would provide a back channel for handling exceptions. So you could use the execution context to trigger exceptions to be thrown. So this is just an example of what. Oops, sorry, wrong button. So this is an example of what it could look like. This is just something. So this is kind of similar to what we do in the cycle interface, because we have a one-way execution. We have to handle exceptions being thrown back. So this is an example of what it could look like. It's not necessarily what you would choose to implement it like. This is one way you could do it. So essentially here, you call execute on this executor, and it throws an exception from inside. Obviously, there's no future to propagate the exception to, so that would be caught and handled by the execution context, in which case you could then maybe call something like throw that would then handle it as an exception pointer. Okay, so in summary, the unified proposal for executors essentially means that you can write generic applications for execution that target a diverse range of different resources underneath with this large amount of customization. And they are coming soon. Thank you very much. I should have some time left for questions.
First question, what does soon mean? Second question, is there library?
Okay. So the questions were how soon is soon, and is there a library? So there are some implementations by those in the executors group that are working on it. They're not complete implementations. They're more for prototyping. So we'll hopefully be looking to start working on something at some point, maybe once it becomes a TS. So there will be implementations coming soon, particularly after it's formed an executor's TS. In terms of soon, it depends on how quickly this goes through the standards committee, I suppose. But we feel we're very close to a consensus on the design. Michael.
So if this goes to a T, let's say it gets approved in the next meeting, that will be November. Those are both immediately to ICE to Geneva. I assume a TS will come out by summer, right? When we go to Rapid Show in Switzerland. If it doesn't get approved, and this is the third round trial, and this happens all over, right? It will be multiple rounds. It will not. It will be San Diego before which is the end of next year before it comes out. So either way, I think the implicit answer to the question is: does it have a good chance that it can C++? I think it has an excellent chance that it can C++.
Question here?
So it might be an earlier version of the proposals, but at one point there was an observation that a one-way executor could be turned into a two-way executor by wrapping it with a future and promise. What happened to that?
So this is still in the proposal. Unfortunately, I didn't have enough time to fit examples. Sorry, the question in the microphone. So originally the proposal does have this idea of adapting executors, but I didn't have time to fit this into this talk. So essentially the idea is that you can have one executor that can be adapted to another executor. So maybe have a one-way executor that's adapted to a two-way executor. So an implementation of executors may provide certain execution functions, but not others. So an implementation can choose to adapt an executor to another type. So when you do a require, it'll say I don't natively support this executor, but I can adapt it. And this is something that can be queried through type traits for the executor type. There is still some things we're trying to figure out about some of the concerns about what happens when you do adaptations. Like for example, if you adapt a two-way executor to a one-way, what happens to the future? Does it just get dropped, or does it be handled in some other way? So we need to be careful about how we allow adaptations so that users don't accidentally shoot themselves in the foot by doing something they don't expect. Hi.
For you.
I guess I have two questions. One is that there's executors in the networking TS, and have you guys started thinking yet about how to bring this proposal and the networking TS together?
So the question was, how does this relate to the executors in the networking TS, and if we thought about bringing them together? So one of the major contributors to this executor proposal is Chris Kolhov, who works very heavily on the networking TS. So the idea, as far as I know, is that the networking TS will be updated to match the proposals in the executors TS. So that will be brought up to date with what we've been doing in executors.
And my other question was the coroutines TS. Obviously, execution and coroutines, they intersect. I'm sure in interesting ways. Has anybody thought about that yet?
So the question was, how does executors relate to coroutines? It is a very good question. It is something that we've got in our minds. We've not spent too much time on that yet, but it's something we will be looking into later down the line.
One that you described at the very beginning, concept of instruction stream. I wonder if this could be heterogeneous, so that on main execution, you run different kind of execution resources. You can run different kinds of instruction streams. Different hardware use different sets of things it allows you to do.
So is the question, can the instruction stream be running on different resources, so like code for different devices? If I don't understand you right. Okay. So
I would think that a modification to this question that would make more sense is let's say I submit a lambda to a GPU resource, and it needs to be compiled into a different assembly. Can the compiler know that?
Yeah. So the question is, how, if you were to say have the instruction stream that you want to execute on a GPU, how would that be handled? So the way this would typically be handled is that you'd have to have another compiler that compiles the code for a GPU. So this would work very similarly to how, for example, we have a SYCL parallel STL implementation where we do this. Essentially, the code that's being executed in the instruction stream part has to be compiled with another compiler that is then linked in with the host application. and then lowered onto some GPU architecture. So it's if you're using targeting something like a heterogeneous device like a GPU, it's not as just straightforward as just having the Clang compiler just compile it and run in the general case. But if you have a compiler that can support that GPU or a multiple compiler approach that can handle the double compilation, then you can do it. Yeah.
Is there a way to specify or to know what kind of requirements that specific compiler or device that you has on your code that you're actually testing? So what you meant is, are you allowed to do everything you know there, or how can you specify what you want to do? You need to use different devices.
So that's the question: is how will there be certain restrictions if you're executing on different devices? And so the answer is yes. So say for example you're executing on a GPU, you may not be able to do things like recursion or dynamic allocation. So the way that will be handled is one of the properties that I showed is this thread mapping. So it could be usually it would be thread mapping, thread execution, where you're executing on STID threads. But there's another option where you're actually executing on non-STID threads. This would be something used for a GPU. And in that case, there's less guarantees that you can make about what you're able to do. Generally, an implementation that supports GPUs would likely provide additional properties and additional traits that can tell you more about what you're able to do inside the code. I think I'm being told it's over. Is there time for any more questions? Okay, has anyone been waiting? I think. So the question: how do you type erase the executors?
The GPU stuff, for example.
Oh, for the GPUs. So the way it would work for GPUs is it's not as straightforward. It wouldn't be as straightforward to type erase because you'd have to have like static executor types that know that these are being compiled by say a different compiler. So it's when you're wanting to execute on something like a GPU, then you would have to have a specific executor type that handles those the requirements to compile and execute with the restrictions of a GPU. So you mean you mean you wouldn't be able to assign it to? That's a good question. So I think essentially you would be able to assign a GPU executor to the polymorphic executor, but then you may not be able to query it for its capabilities anymore. That is a good question. I'll have to think about that. I think I'm out of time for questions. Okay, so we've gone over. So if anyone has any other questions, I'll stay at the front to take questions.